Hello, welcome you to this video. Today we will discuss experiment number 11 based on root locus analysis for various system. So the main objective here is to understand how MATLAB works for plotting the root locus. So the main idea, if you remember, so the root locus actually give us the path of the poles as we increase the gain k. So the first task is to plot the root locus on paper. So as you learn about root locus plotting, so you have to plot it on the on paper, then verify it using MATLAB. So here we have a block diagram of unity feedback system where h of s is 1 and k is part of g of s. So we have to plot the root locus for this. So what we do actually, because using the characteristic equation, we know that we have to use the open loop transfer function for plotting the root locus. So same thing is used by the MATLAB command that is known as rlocus to plot it. So first of all you have to plot it yourself. So there are three systems here. So first one has 1 0 and 2 poles, second one has 2 zeros and also 2 poles, last one has 4 poles and 1 0. So this you have to plot it graphically by yourself, applying all the rules, and then we will check it using the MATLAB. So how we do it in MATLAB? So what we have to open the MATLAB. So I open the script file here. Again I wrote this is lab number 11, clear all, close all, and CLC, so that command window is clear. So this is my task 1. So as we start normally for task 1, what we do actually, we define s using transfer function operator, then we define g1 that has single pole, a single 0 and 2 pole. Then after that I define a transfer function that is g2, then I define g3. So these are three commands that used to define the transfer function that is given in task 1, that is g1, g2 and g3 here. Now after that what I did here, I use a figure, so that I want a new figure here. So I use a plotting command that is known as subplot. So what I did actually, 2 cross 2 means that I want 4 plots on a single figure. So subplot, what it did, 2 cross 2 means that you want 4 plots. So for first plot in those 4 subplots is for root locus of g1, I give the title of root locus for g1. Similarly, second is for 2, I put 2 so that I am plotting the second plot, and I give name of g2 and so on. So it is defined here. When I run this up to this g3, I get a figure and I get this figure. Look here, this is g1, this is g2 and g3. As we know that in g1 we have 2 poles and 1 0, so those are on the real axis, and we apply the rule of real axis that always root locus start from poles and ends at 0, and also the rule of real axis, that is we normally have root locus after odd number of poles are 0. So root locus start from pole and finish at 0. Then there's no root locus in between 0 and pole, because number becomes even. Now again there's a root locus. So this is the first g1. Similarly, g2 has 2 poles, 2 zeros. So as we know that root locus may always start from pole and finish at 0. So it will start from these 2 poles using the real axis rules, and it will have to finish it because it can't travel on the real axis. So it will break out from here and then break in here, and one pole root locus is finish at this 0, other will finish at this 0. So this is g2. Similarly, last one we have actually 4 poles and 1 0. So again root locus, then it is breakout, then we have one pole is finishing at 0 and so on. So these are the way you can verify what you plot and what you get on MATLAB. So this is task 1 that we have to do. Now if I move to task number 2 here, Now we start the task number 2. In task number 2 we have to implement the DC motor that is given in lab 6. So it is between theta and EA, so transfer function becomes 1 over k over s into s plus alpha, if you remember. So I will implement this and see the plot. Now here he wants us to study the pole, closed loop poles with respect to gain k. So as we know that as we increase the gain, it will vary the pole location. So we can do this using PZ map and increase the k. After that we will verify it using the root locus. So this will satisfy that we actually root locus actually give us the locus of the plant, so roots of the plant. So now look here what I did for figure 2. For I make gain is k, alpha is 1 and k star not 1. Okay, commented this is not required. K is 0.001, so I don't want to start from the pole location. I start from a little away from the pole and I make a loop that is starting from this with a increment of 0.1 up to 10. Then I use the G4, which is DC motor transfer function 1 divided by s into s plus alpha. I told you alpha is 1 here. Now I make a closed loop system. For that I use sys feedback k times G4 comma 1 as we see the block diagram of task 2. Okay, so k, g and 1. Alright, now after that what I did here, I use PZ map, so that I want to map the poles when k value is 0.0001, then 1 and so on. So then I hold it so that I want to plot it for all the loop variation that k start from 0.001 to up to 10. Then I hold off it and then I plot the root locus. So what is my thinking, that as I increase the gain k, I get the same structure of root locus, because root locus is doing this for me. Instead I have to do all this for myself and applying the loop. So this is the main idea. This tells us that root locus actually location of pole with variation of k value. So when I run this task number 2, I get this figure. First one, this is for PC map, which is due to the loop. So starting pole values here, second one here. So I will start from here. It come and go. One is going in this direction, other is going in opposite direction. So this is the pole location when I vary k from 0.001 up to 10. I don't want to do it up to infinity so that my system is hanged. Just do it to understand and get the idea. Now this is one way of doing it, but the easiest way is using the root locus command. So root locus will give me the same thing. Look here, it will start from these poles and goes in that direction and in that direction. So this means that if I choose any point here, this give me different values of gain here. So look here, I have different values of gain and different pole locations. These poles are different, these poles are different. Similarly I can see here, so we have a different gain values and different pole locations. So this is closed loop poles, okay, when I close the loop. So this is the main idea about root locus, how you use it in using MATLAB. Now we use another toolbox that is available for control design, is known as SISO tool, means single input single output. SISO means single input single output toolbox. So when I click this, so there are two windows opened here. This is the first one and we have the second one, this window. So these two windows will open. So if you look here in this window, if I use and say import, so I can import the transfer function here. I browse it, for example G4, I say import and then close, then say OK. So it will give me the root locus plot. Also this is bode, we will study it later. So this is phase magnitude and this is phase and this is closed loop bode. Okay, now look here, if I can move this will move the gain and also tell me the root location. So How this toolbox work? This toolbox work on this architecture here. F is the forward function, C is the compensator, and G is transfer function, H is our feedback. So I can change the control architecture if I need. So there are different architectures available. Okay, you can use anyone for your own design modeling. So now commonly use this one. Okay, so this is one thing we can do here. Second is the compensator. So this is the compensator value that we have. So for example, if I move my pole location on body plot, for example here, if I say import and I import if I say browse G4, import and then close, then okay. If I move this here and then I go to next window where I see the compensator, so it will give me the values of the compensator. So next thing, we have a graphical tuning method. If you want to tune it using root, locus or any method. Then analysis plot, because if you are interested in plotting the step response, so I say okay, plot 1, I want to plot the step response for closed loop R to Y. So look here and it will give me the step response. So as it is an interactive one, as I move the location, it will also update my step response in runtime. So this is one thing that I can have. Similarly, if I want to see another plot, second one, and I want to see what you say step, not step, if I want to see second R2 input to the controller output, so I get another figure here. Look here, this is the control input to the system. So these are some plots that I can use. Then there's another thing is known as optimization based tuning. So you can optimize your compensator here. So this actually I've used for designing compensator. So if you do that, so these are the steps. You have to select the compensator to optimize, select design requirement, then you have to set the optimization option, then you have to use the optimizer, then view the result. So for example, I have a compensator, so what I want to optimize is C. All right, then I say design requirement. If I have, I can add here. Okay, if I want to add some design requirement, so I can add new design requirement. For example, if you want rise time, settling time, you can add here and say okay. So these are the requirements for controller design. This is known as specification. So I put here. Then you have to go to optimization. If you want to do some optimization formulation, you can put here. Now start the optimization. So now this is what we are getting here. This last one is the optimizer graph. I don't know why it's not. It took some time to do the simulation. Look here, it will try to fit our result in the constraints. So SISO tool is used here to design optimize compensator. So this SISO tool have lot of possibilities here. You can add any type of controller here, lead, lag, notch, or you can introduce zero, integral or complex poles for control compensator design. So this helps a lot. So in next video I will discuss further about this SISO tool. Thank you.